Welcome back to lesson 2.2. We're going to look at different ways to visualize our raw data. And the first is going to be a histogram. Then we're going to look at frequency polygons and also other distribution shapes. So a histogram is a graph that displays the data by using contiguous vertical bars. They touch each other because our data goes in sequential order. And they have different heights that represent the frequencies of the classes. I'm going to show you another picture. So this picture here shows the record high temperatures, and from the smallest was in this group, a class of 99.5 to 104.5 degrees. And there were, it looks like 2 that fell in that. So it's taking our frequency distribution that we created in lesson 2.1, and we're going to put it to a picture form. So if we go back to the notes, F stands for frequency and N is the total number of data values that we're looking at. And the relative frequency is F divided by N. So to construct a histogram, frequency polygon, and an ogive, there's some similar things that we need to do for each of them. You're going to draw and label the X and Y axes. On the X axis, label the class boundaries of their frequency distribution for the histogram and ogive, and label the midpoints if you're doing a polygon. Plot the frequencies for each class and draw the vertical bars for the histogram and the lines for the frequency polygon and ogive. So we're going back to the data that we looked at in lesson 2.1 that was regarding the world's 30 tallest buildings. And we just created this together with our frequencies and cumulative frequencies, and we created our boundaries. So now I've taken our limits and our boundaries and put our frequencies in our table all in one, and we're going to use this to make a histogram. So I set up the scaling for us. So the scaling is down below. So this is the number of stories. Tall for the buildings. And then over here, this is going to be the number of buildings. The number of buildings. And so our first boundary is 53.5. And so I'm going, these are going by 5, 10, 15, 20. So this is going to be 50 right here, and 55 is right here. So it's going to be right in about the middle there. It's going to start the 53.5. And then it's going to go up to 62.5. And so that'll be in here. So that's going to be about how wide my bars are going to be. And then the next one is going to be, and there were 7 in that frequency. So it's going to be up to the height of 7. So I'm going to draw on here. I get colored into that. And so that's the 7 there. And then the next one goes up to 71.5. And there were 6 in that group. So that's going to go over to 71.5 and down. And then the next one goes up to 80.5, and there were 8. I'm not very good at drawing freehand. And then we go up to 89.5, and that is, there were 4. And that right here. And then up to 98.5, there's 1. Then there were 3 up to 107.5. And then 1 up to 116. So that is what our histogram would look like. For the heights of the tall buildings. You can make a histogram of Desmos by these instructions. And then also if you go to your virtual book, in the back of the lesson, there is a description on how to make histograms in Excel and Minitab as well. So let's look at another one. The next one is the data on the shoe sizes of 50 male students. The sizes are continuous data since the shoe size is measured. Now, we talked about this in class. I would not say that this is continuous because the data is either 9 or 9.5. There's no 9.235 or whatnot, but the book has chosen to use this as continuous. I'm doing this for the sake of drawing a histogram. So suppose you choose 6 bars. So in Desmos, I put my data into a list, and then I typed histogram with X1 and 0.5, and that X1 is telling us where the data set is, and then this is how wide I want my bin width, because I want them in half sizes. And then you can also tell in Desmos if you wanted to use the frequency, which is the count, or relative frequency, or the density. And then if you want it to be aligned in the center or the left, that's up to you. And this is the shape that it came up with for the shoe sizes. So I also did another one in Desmos with our data. And this is the data that I came up that I had used for our 30 tallest buildings. And this one's a little bit different because I told it that I wanted to have 9 groups, and then it set it up just like we had it in ours. Except for because of the groups, the way it set it up, our frequencies are just a little bit different because it puts the boundaries at a little bit different boundaries than the way we chose ours. So let's go to example 3. I want to show you another one. Using this data set, construct a histogram. So we have the number of hours my classmates spent playing video games on weekends. And so they're listed here. And then if I put these into Desmos, and again, this is what it came up with. I told it I wanted to have 1, 2, 3, 4, 5 classes with a width of 5. And we're going to be talking about shapes of distributions, but it's great to kind of talk about this as we go. This would be considered a J shape as far as the distribution goes, but more specifically, we would say that this is a skewed left data set, and we're going to tie into this later on in lessons, some other chapters. But since we're looking at shapes now, it's great to bring those up. The last shape, I'm going to just pull this one back and say that this one looks pretty symmetric, except for this skew, this outlier data piece out here. Next up is making a frequency polygon. So here's an example of a frequency polygon. Frequency polygons are a little bit different than histograms because they use the midpoints of the data instead of just the class boundaries. So frequency polygons are a graph that displays the data by using lines that connect points plotted for the frequencies at the midpoints of the classes. The frequencies are represented by the heights of the points. So 102 in this particular data set, 102 would have been the midpoint of that class, 107 would be the midpoint, 112 would be the midpoint, and so forth. So they are similar to line graphs, but have a fake first class that touches the x-axis. So that's one thing, is we have a fake first class. So we have to pay attention to that, fake first class. And then also, we need to know how to find our boundary midpoints. So our boundary midpoints are found by taking the lower boundary plus the upper boundary and dividing by 2. And we're going to do that here. We're going back to the data on the world's 30 tallest buildings that we've worked with already. And we're going to find the midpoints of these classes. So to do that, we are going to take 53.5 and add the upper boundary of 62.5 and then divide by 2. And we find out that that midpoint is 58. And then likewise, we would take 62.5 plus 71.5 and divide by 2, and we would get 67. Now, when we found these in lesson 2.1, we said that our width was 9, and that's true between the lower limits, and then also 9 between the upper limits, and that also holds true between the midpoints. So the midpoint should be 9 spaces apart. So once you found 1 or 2, it's easier to find the preceding ones. So the following ones, I should say. So we have 58, 67, 76, adding 9 gives us 85, adding 9 gives us 94, adding 9 gives us 103, and adding 9 gives us 112. And then we have to remember the fake first class. The fake first class is going to be 9 above the 58, which would be 49. So we're going to go and make frequency polygon. So my fake first class is going to be at 49. And that's going to go right here, a dot on the axis. And then the next one is going to be at 58. So I'm just going to mark 58. It's going to be right here. And that's actually going to go at the height of 7 because that's our frequency. So I'm going up to 7 and going across to where it meets about 58. So 7 and 58. And then the next one is going to be the midpoint of 67, and that's going to have a height of 6. And then the next one is going to have a height of 8 at 76. And then 85 is going to have a height of 4. 94 is going to have a height of 1. "103 is going to have a height of 3. And then 112 is going to have a height of 1. And then, of course, we would connect these. And there are computerized, sophisticated ways to do these. Making the first one by hand, though, always helps you think about how it's actually made and solidifies that understanding better. And then the ones after that can be easily made by the computer by putting your data into Excel, Minitab, Desmos, things like that. Actually, it should have a fake class at the end as well. So this should be at 121. So that would happen down here. So that would be our frequency polygon. So a frequency polygon was constructed from this table below for calculus final exam scores, lower bound, upper bound, frequency, and cumulative frequency. You can see that there were 1, 2, 3, 4, 5 classes. So then we've got a fake first class, 1, 2, 3, 4, 5, and then a fake last class. Okay. And you can see the markings for the frequencies are at the midpoints again. Frequency polygons are useful for comparing distributions. This is achieved by overlapping the frequency polygons drawn for different data sets. I'm going to show you that one here. You can see in this example number 6, it says we will construct an overlay frequency polygon comparing the scores from example with the student's final numeric grade. So we've got the calculus score and then their calculus final grade. So their final test and then their final grade. And then we overlap that for frequency polygon. And you can see that they followed about the same distribution. And then lastly, I just wanted to go over some different shapes of distributions that we may come across this semester. This one here is called a symmetric shape. Symmetric meaning it kind of looks like a bell where you could, looks like you could cut it in half and the two sides should match. This next one is called uniform, and it also looks like it's symmetric, but it's more like they're all about evenly spread out. These next two are called J-shaped, and that's because they kind of look like a J or a reverse J, but also we can see that they are going to be called skewed in our next later on lessons. And here are some other ones that are skewed as well. And you can see that they kind of start to look symmetric, and then all of a sudden they're kind of pulled out into one direction. The direction where it gets thinner is what we're going to identify. So it's thinner to the right, so it's considered right skewed. And this one is thinner to the left, so it's considered left skewed. And then the last two, this one is called bimodal on the left because it looks like there's kind of a group of data down here on the bottom, and then there's also, it looks like a separate group here on top. And then last but not least is the U-shaped group. something like this. The ones that we're mainly going to deal with this semester are going to be a symmetric and then the skewed left and skewed right. Catch me back for another lesson.